Good day, everybody. Today we're going to look at Jefferson's method of apportionment, the first one used by the United States, and it was used from 1790 until 1830. And a quota violation was noticed, so they stopped using it after that. But it was used primarily because in the Constitution, specifically Article 1, Clause or Section 2, Clause 3, they stipulate how to apportion. Well, they gave some rules. The major rule being the number of representatives for the House shall not exceed one for every 30,000 people. But of course, each state shall have at least one representative. So looking at that, we can try and do an apportionment, and this is the House of Representatives' first attempt at a apportionment. So using 30,000, they divided each state by 30,000, right? You can have up to one representative for every 30,000 people. So divide by the 30,000, and Connecticut would get 7.89 and so on, but you can't do fraction of people. So they had to round down because otherwise you go above the or below the amount, right? So we're allowed one representative for every 30,000 people, and this is what would end up happening, right? So you'd have one representative for every 33,000 in Connecticut, for every 55,000 in Delaware, and so on. So no state has more than one representative for every 30,000 people. If you round down, if you went up, then that would probably be violated. So using that 30,000 and then rounding down, it would turn out there would be 112 members of Congress. So nowadays we fix that first, but then they fix the divisor first. But looking, now that we know there's 112 seats, we can then look at, well, if we were to divide that 112 fairly, then each state should get the fraction of its population divided by the total country's population times the 112. And if you do that, Connecticut should get 7.34 seats and so on. Notice the big state of Virginia should get 19.53. That would be its fair share of 112. If you take its population over the country's population times 112, you get 19.53, but it's getting 21. So I guess that was noticed, although this is essentially Jefferson's method, and they didn't put 1 and 1 equals 2 until 1830 when it happened, that you can have an upper quota violation, right? Because this would be an upper quota violation. You should get 19.53, so maybe you could get 20, but certainly not 21 seats. Anyway, let's look. So that was in the House. In the Senate, they used the number of 33. So again, same idea. Just pick a divisor, divide in. So this would be sort of one representative for every 33,000 people. Divide each state's population by that divisor. You get these fractions. Round down. You have to round down, or else you'll go more representatives for every number of that. Anyway, so if they round down, now there's 105 seats to be given out, and then you can see the how many people per seat for each state is given right here. And if we were to look at what's the fraction of what each state should have gotten out of 105, so just take Virginia's population divided by the country's population times 105. Its fair share of 105 would be 18.31. That's a little closer. And in essence, this is Jefferson's method. So they were doing it at first, before it was, of course, called Jefferson's method. gradually the House and Senate decided, well, why fix the divisor first? Let's fix the number first. And they fixed it at 120. If we go back to the 30,000. Oops. Notice this, right? This fraction here is about 120. It's a little more, 120.53. And what they did, I have here, and well, if I use that 30,000 again, I get 120.53. But they went to the lower quota, and that gives 112. And then they looked at this fractional part, and well, to get to 120, you want to get to 120, you then give out seats based on who has the largest fractional part. So the largest fractional parts are all here, and then that will take you to 120, and that's called Hamilton's method. So if we change the standard divisor to make this exactly 120, so that'd be the standard divisor, a little bit off of the 30,000, but now the standard quotas add up to 120. If we go to the lower quota and then give seats based on the largest fractional part, we get Hamilton's method of 120. But now there are states that have more than one representative for every 30,000 people. Right? Connecticut, it's going to average one representative for every 29,605, and so on. Delaware, 27,000. So that went against the Constitution, and Jefferson honed in on that and wrote a slightly long letter to George Washington, opinion on the apportionment bill, and he's going into that 120, the apportionment, and then certain states, this is their average of people per representative, and these states satisfied that requirement in the Constitution. And so he essentially convinced George Washington that it was against the Constitution, so he had to veto it. And that was George Washington's first veto, his only veto for his first term, and Congress couldn't override the veto, so they went back and redid an apportionment using 105 representatives. And again, the way they did it, we call Jefferson's method, where you take a divisor. I think 33,000 would work. We already saw that with the Senate. And then when you divide each state by that population, you get this quota. If you round down, now you'll get the 105. And no state will have above one representative for every 30,000 people. So this is the first apportionment of the United States in 1790. This is the one that was used. Just to compare with Hamilton's method, if we want to give out 105 seats, you take the total population, divide by 105 seats. That means on average for the country, there's one representative for every 34,437. And if you divide each state by that amount, you get this quota. You go to the lower quota, you round down, that's the lower quota. And you look at the fractional part. So if you give state seats based on the largest fractional part, this would have been Hamilton's method. So there's a difference in Delaware. Poor old Delaware. Lost a seat, and Virginia gained a seat. So what's called Jefferson's method, where you just you find a divisor and you always round down, that's going to favor large states. So that's the difference. Notice with Delaware's population, there'd be no way you could get two representatives if you can have at most one for every 30,000 people. So Delaware, thanks to that rule, was kind of stuck at one. Anyway, so there's the population. Again, notice with Hamilton's method, again, Delaware gets one representative for every 27 or 2,800 people, 28,000 people. And all the other states are okay. But with Jefferson's method, no state has more than one representative for every 30,000 people. If I want to look at the 2020 population and use Jefferson's method to apportion 435 seats to our 2020 census, I've got the census numbers in here. Notice right now I have 413 seats. This would be the standard quota. So I need to divide by a smaller number to get this amount up. So let's go to, say, 750. That just went up a little bit, so you just got to keep trying. We'll try 730. Getting there. Let's try 720. And then that worked. So you just keep dividing a state's population by this divisor. It'll be smaller than the standard divisor because you're going to round down. You call this the modified quota for this new divisor. And if you round down, you can never go below the lower quota, right? Because this modified quota only goes up when I divide by a smaller number. So here's the standard quota. The lower quota would be 6. Well, if you divide by a smaller number, this goes up, so you'll never have a lower quota violation. But if we look at California, you can have an upper quota violation, right? So if I divide by a smaller number, this number gets bigger and bigger. And in this case, it went to almost 55, but the lower quota is 54. But still, that seems like that's more than it should be. In California is at 52. 52 seems pretty fair. Maybe even 53 if you're being generous, but 54 is ridiculous. The second biggest state also got an extra seat, Texas. Its standard quota is 38.3, so it should get 38 or 39. But in the end, dividing by that smaller number, it really affects the bigger states more. And it went up to over 40, so then that when you go down, it'll go to 40. And this is what actually happened in 1830. New York had a standard quota of 38.6, so it should get 38 or 39, but in the end, with Jefferson's method, it got 40. And that apportionment was used in 1830, but no more after that. And they're like, nobody was really happy that New York got one more seat than its upper quota. Related to Jefferson's method is what we call Adams' method, and that's instead of rounding down, why not round up? So if I were to round every standard quota up, I will get a number too high. Oops. Let's look at this. Well, yeah, 461. So we need to divide by a smaller number. I mean a bigger number. Let's go to 790. So notice in this case, you won't have an upper quota violation because all these numbers are going down. So if you take the standard quota and round up, you're at your upper quota. If you divide by a bigger number, then you're just going to have a smaller number to round up to. So you're not going to go over your upper quota. So we're at 441, so I need to divide by bigger numbers still. Let's go to 800,000. So at 800,000, we're at 436. I'm getting close. Let's try 802,000. There we go. So we made it to 435. So here's the standard quota. That'd be the fair amount if you could subdivide people, or the 435. But dividing by a bigger number than rounding up. Notice Texas now gets 37, and so it has the opposite problem with Jefferson's method. Instead of being above its upper quota, it's now below its lower quota. Right? It should have gotten 38 or 39, would seem to be most fair, but it's below. And similarly with California, the other big state, 52 seems pretty fair, 51 worst case, but instead of 51, it got actually 50. So below its lower quota, even though it's pretty much at 52. So you can now have a lower quota violation. It's kind of the inverse of Jefferson's method. So yeah, so there's that method, but because of these quota violations, they're not too popular, but they do have some optimization properties, which we'll go into in another video.